So here we are, week 10. I'm going to go through a series of examples. I'm going to tell you when I started this lecture, planning this out 2 days ago, I thought no big deal. I'll make up an example of each a beam and column for wood, steel, and concrete. I haven't done this lecture before. Up until 2 years ago, Structures 1 and Structures 2 were each only 10 3-hour lectures. In fact, when I started, they were 10 2.5-hour lectures. So the time has grown. And in the past, there's always been at least something that has made us miss one particular class. So last year, COVID, there was a week that it was just impossible to make things happen. The year before, I had strep throat for the 7th time in 6 months. And then the year before was when you got hit by the car, Dave, and I was pregnant and still had a 18-month-old. So there's always been a reason one lecture has kind of fallen off and we've only had 11. So one good thing about doing the asynchronous stuff is I have no excuses. I have to get all 12 of them done. There's no way we can, it was always like we couldn't get another room or they wouldn't give us the extension. Like even though there's time you can extend until, they would never give it to me. So I sat down to make these and I'm not done. I've got the steel examples done and the wood examples done. So I'm going to go through those as much as I can right now. I still have to make the concrete one, so I apologize that you're not going to get everything today. I feel like we've done pretty good, and considering COVID asynchronous craziness, we're going to be 1/3 of a lecture delayed by a day. So hopefully you guys can forgive me on that. But I took away a whole assignment for you, so that's pretty good. Last I checked, it looked like reciprocal frames were leading the way on the voting list for what lecture you guys wanted to hear. I'm thinking we're gonna do that lecture next week and the beam testing the week after. It's of no difference to you. You have until the end of, or until the day of the exam to fill out whatever that small beam testing questions will be. The answers will literally be in the lecture, so you'll have weeks to go back and fill that in if you want to. Simply because we haven't got the concrete beams fully made yet, and I was hoping to test them on the weekend. I have a friend of our family's coming over. Their 8-year-old son is really excited about structural engineering, so he's going to replace all of you as the audience that's live. So all the questions I would normally ask you guys, I'm going to ask him, just to really show how much of it is intuition. And he might get some of them wrong, but the idea is that there's someone to communicate with there. But I don't have the beams made yet. So it'll probably be in week 12, and next week Dave and I will record our reciprocal frames lecture for you guys. So let's get started. What I've done is I've gone through a worked out example from drawings all the way through for these different elements. Do you guys remember way back at the beginning of Structures 1, I showed you a really weird building, but it was a good building because it showed all the different things. There's many of the different things as I could think to throw into one building. No one would build this building, it was stupid, but it showed a lot of the structural intent. Well, I've picked a beam and a column from that we're going to design. I have re-uploaded that drawing set to Quercus as well, so you can find it in there. So let's take a look here. We've got our steel column. So this was our basic steel building, and we're going to look at column C4 from level 2 to roof. And if you look at that full drawing set, you'll see that the difference between level 2 and roof is 3 meters. So I'm only in this showing the roof, but you could open that drawing set and see what that difference is. I am probably, well, I think you guys can see this. It's not as great as I would like, but it's a little bit bigger than a little dot. This, I can't write on this sheet. I'm not going to do handwritten versions of this because I've created really good PDFs that I'm also going to upload. And I think it'll help this go a little bit faster because I think otherwise this could end up being like a 4-hour lecture. And I think where this is a review and you'll have access to this, I just kind of want to talk through the process a little bit. The calculations, I'm not going to plug into a calculator. You can see those written there. But I can't, whenever I write on the PDF screen for you guys, I then can't make it function properly. So I'm going to have to use my mouse and talk through it. So this is column C4 from level 2 to roof. So column C4 is right here. So I've circled it. This is our roof framing plan. And we can see that we've got this grid dimension here and these grid dimensions here. It looks like it is picking up roughly 1/4 of this bay and 1/4 of this bay. I know that this beam technically goes to here, but we're going to ignore that and it assumes it goes all the way over to here for right now, simply because I didn't notice that when I was doing it. Making it a little bit more conservative, not a problem. If you guys remember, there's a column schedule listed with this as well. We have loads here. There's a snow load. They've already worked it out from SS and SR and showed us 1.12 kPa plus ASL as shown. There was no ASL shown on this, so it's 1.12. And then here's the dead loads. So everything we need to design this, we have. Let's go to our next page here. All right, so if we were following our sizing guidelines, we'd take that height and divide it by our sizing guideline for steel columns, or 3 meters divided by 20, and it tells us 150 millimeters. So for a preliminary drawing set, we would probably want to draw an HSS that's 152 by 152 on our drawing set to leave us a buffer. Now, from what we learned in Structures 1, we know that we can take these loads, figure out what the uniformly, or we can figure out what the UDL, which is the factored dead load and the factored snow load. In fact, this should be snow. So the factored dead load and the factored snow load. And we can look at our tributary area, which was the kind of 1/4 of each of those bays. So we have a factored load of 3.33 kPa and a tributary area of 40.5 meters squared. Remember, I ignored the fact that the stairwell was there. So don't worry about that. I'm going with 1/4 of each of the bays. I can multiply my load times my area, and I get a factored load of 134.9 kilonewtons. I know I have an unbraced length on my column of 3 meters. So it's always nice to draw yourself a little picture. Here's my free body diagram of my column. I've got PF, which the value is listed right here. I've got my dimensions, and I've got the reactions that make this stable. That is everything we learned in Structures 1. I know, it seems a little sad when it's written down so quickly there, doesn't it? Now we can look at what we've learned in Structures 2, which is actually designing it. Well, we know if we have a table, we might as well use it. You guys have to do some full calculations in the exam. We have to. But what we want is a PR greater than PF. We know what PF is for this unbraced length. We've calculated it. Well, if we look through all of the available, we're going to go with a square HSS. No one's told us that, but let's just stick to a square HSS. We can go through, you're muttering to yourself. Is everything okay? We have an HSS 76 by 76. And all of these columns list at 2.8 meters and 3.2. We're at 3 exactly, so we want something that's going to fall in between there. Well, it looks like we might not be able to work with a 3.2 wall thickness because we have basically 135. But it looks like an HSS 76 by 76 by 4.8 would fall in between 151 and 182 for our CR. And remember, we want CR to be greater than CF. So we can interpolate here and figure out what it is as a straight line value between these two things. So we can come over here and interpolate for a 76 by 76 by 4.8 HSS, and we get that CR is 166.5 kilonewtons. That looks like it's greater than our CF. Now, I wonder, do I have, look at this. I'm going to open these up right here. We're talking about column C4, right? So here's column C4. I have 150 kilonewtons written down here from level 2 to roof. Sometimes we'll just round up to something even, having a little buffer in there, no big deal. We know that if it's critical, we can go back and refine it. And that maybe that 135 kilonewtons gets us the exact column that we want. But look, I have a 152 by 152 by 8. Why would I do that? A 76 by 76 by 4.8 works, and it worked kind of comfortably. Why would I make a bigger member? Why would I do that? Well, there's two reasons. Part one is that we have a second part to this column down here. Now below, we have 450 kilonewtons on this. So you might still say, who cares? Make this part be a 152 by 152 by 8, but not this. And I get it, this would be very annoying to you, but this is where understanding construction can actually come into play. Designing or structural analysis isn't the only component. So we're going to go through the calculation for the 76 by 76 by 4.8 thoroughly, but the reason that's not what's on my drawings is because most of the time columns will come in at least a 2-story lift. Piece count can be a big part of cost, and sometimes they don't like to then just build one floor and then come back and put more columns on. Columns they might put in place and have them go more than 1 story, build in the second floor, and then put on the roof. Not always, but for something like this, for 2 stories, they probably would do this. So I know that inevitably the contractor's going to come back and want to do that. So I'm just going to go with that. I know this is going to make it cheaper. It's going to make it easier for them to build. And that is part of my job as well. As much as I say size is the be-all, or cost is the be-all and end-all, and that's usually directly related to the weight. Sorry, I put my eyelash in my eye. It's not the only thing. Ease of construction and piece count can come into play. Oh my goodness, sorry guys. So, sorry. I've got an eyelash in my eye.
I know, I got it.
Oh, now I'm probably going to sneeze. So in this case, I made a judgment call, and also we have 152 by 152 in most of the locations. Sometimes just having a standardized column can make things easier as well. So some of this is experience. But we're going to now do the calculations for the 76 by 76 by 4.8. Just because that's the size, we want to verify that. So we're going to go through and do that calculation. I need to stop this. I can't get it out of my eye. Sorry about that. I think I've gotten it out of my eye now. Okay, so I get it. How do you decide? Well, I'm going to tell you that that would be my job to help inform you of that as the architect and me being the engineer. So we're going to go through and we're going to design the one that we just sized. So let's go to the third page where we actually go through the calculations for an HSS 76 by 76 by 4.8. That is 3 meters long. Well, we know everything we need to know about steel. We know the reduction factor for a steel column. We know that cold rolled steel is 350 MPa. We know E is 200,000 MPa and G is 77,000 MPa. We know that we can find the member properties. We can open the steel sections. Eventually. That's weird, right? That it isn't showing up, right, team? What's happening here? There we are. So we can go to the page that has the 76 by 76 by 4.8 on it. And on that page, we can look up area, we can look up I. Now, is it IX or IY? One of the great things about a square section is it's the same in both directions. We can, well, we're not talking about bending, so we don't care about S and Z so much, but we know we need R. So we can look up the shape properties that we need to go through our calculations. So I've got that written here. I've looked up area, I've looked up IY or IX, it doesn't really matter, it's I, and R. We know the unbraced length, and we know K is all about what the end conditions are, or it helps modify the unbraced length, but I'm only giving you ones that have a K of 1. So now we can start determining what CR is. We know that the equation for CR is the reduction factor times a shape property, which in this case is area, times the strength of the steel, times some factor that talks about buckling. We know that that is lambda for us. We can go through and calculate lambda. And so that's just plugging in the numbers that we have up above. And then we can calculate CR. CR is 165,437 newtons, or 165.4 kilonewtons. And then we always like to write out, does our column work? Well, yes, we have CR of 165.4 greater than a CF of 134.9, and it works. Now, there's a 0.1 kilonewton difference between our calculations and the table. Remember, on the table, they calculated CR at 2.8 meters and 3.2 meters. We interpolated between those 2 points when we did it based on the tables. It's going to be pretty darn close to the full calculated version for 3 meters tall, but we've now gone through and done it in the very refined calculated way, and you can see that it's almost exactly the same. That wasn't so bad. We've done our first example now. So I'm going to save that. We'll keep our steel sections open, and let's open our steel beam example. Oh, didn't like that, did it? All right, let's open our steel beam example. I can tell you it took a lot longer to make that. I can do these calculations very quick, but I'm not normally trying to write it out and find ones that are going to give you the best information that I can possibly give you. All right, let's look at our beam now. So it's the same building, same roof plan, and we're going to design RB11. You can see here it spans from column to column. It's 9 meters long, and it's picking up the load from half of these joists and half of these joists. So its tributary width is going to be half of this 9 meters and half of this 9 meters. Let's pop over to the beam schedule and see what it said I sized it as. So RB11, we had a beam schedule. RB11 was sized as a W410 by 60. So that was me using structural analysis software. Let's go through our work for this. Well, let's start with our sizing guidelines. Our sizing guidelines for a steel beam, and so a steel beam is the type of bending element in steel that is usually doing the second hardest job. The easiest job is joists or purlins, and they're usually just picking up deck and are some regular spacing apart. But a steel beam is the beam that is usually picking up joists or purlins, and that looks exactly like what we had. So the sizing guideline for a steel beam is L divided by 20. We have a beam that's 9 meters long, divided by 20. It says that we should have a depth that is at least 450 millimeters deep. We know that the closest or the biggest available steel beam category after that is a W460. So on our preliminary drawings, we'd probably want to allow for a W460 beam on our drawing set. Well, now let's move on to actually producing contract documents. What would we put in our drawings? Well, we know that we have a uniformly distributed load on a simply supported beam. And for that, our reaction equals our shear, which is W times L divided by 2. The moment is going to be the peak at the center, and it's WL squared divided by 8. And the deflection is going to be max at the center, and it's going to be 5 times W times L to the 4 divided by 384 EI. This is stuff we did in Structures 1, and you have these beam loading tables. We've already calculated out our dead load, and we've calculated out our worst case factored load, which was 3.33 kPa. We did that for the column that was going from L2 to roof. We can now figure out the tributary width. We know the tributary width was half of one bay plus half of the other bay. So 9 divided by 2 plus 9 divided by 2 equals 9. That means our uniformly distributed line load on this simply supported beam is our load times our tributary width. So 3.33 times 9 meters equals 29.97 kilonewtons per meter. What we're saying is that every meter of that beam needs to be able to pick up almost 30 kilonewtons. We also know that serviceability can be a pain in the butt, and we need to track a few other uniformly distributed loads. We need to be worried about our serviceability dead and snow load case and our serviceability snow all by itself. Now, normally we've been calculating that by ourselves, but we've seen kind of consistently that the only difference is what importance factor is on it. So I'm just going to multiply that 1.12 by the importance factor right here. So I've got 1 times the dead load plus the importance factor for serviceability times the snow load equals 2.33. And for the snow load serviceability case all by itself, it's 0.9 times 1.12, or that importance factor for serviceability times the snow load. That means I can calculate the uniformly distributed line load for dead and snow and for snow by itself. So I can calculate those here. I'm going to draw myself a free body diagram. It's always good to draw a free body diagram. I've got my reactions for a simply supported beam. I've got my line load. Here I've called it WF, and I've shown what this dimension is. That dimension is important. That lets us see at a glance kind of what scale of things we're talking about here. I, now knowing my uniformly distributed line load and how long this beam is, can start calculating my maximum shear, my maximum moment, and my allowable or my maximum allowable deflections. We already saw that for a uniformly distributed line load on a simply supported beam, we multiply WF times L divided by 2, and we get 134.9 kilonewtons. we can draw it here as our shear force diagram. Here's our bending moment diagram, and the worst case moment is WF times L squared divided by 8, or 303.4 kilonewton meters. And we know that steel with finishes that can be damaged, because it's a ceiling, there's maximum allowable deflections. We have L divided by 240, or 9,000 divided by 240, giving us 37.5, and L divided by 360, or 9,000 divided by 360, for 25 millimeters. We can calculate what I required we would need based on these deflections. So this is something we did learn this year. We learned that we can calculate the allowable deflection, or we can calculate the I required to make sure we don't exceed the allowable deflection by rearranging this equation they gave us up here. This is the delta max. Well, we know what delta max we can see. We have that from our serviceability charts. We know what W is, we know what L is, and we know what E is. We could calculate what I required we need, or what we need to make sure our beam does not exceed these maximum allowable deflections. So this is just that equation, 5 times the line load times L to the 4, and L is in millimeters here. That's crucial. And these are our serviceability loads. So I'm going to do this twice. I'm going to do it with dead and snow, and then I'm going to do it with snow by itself. So these are the corresponding line loads. And then that's divided by 384 times 200,000 times the appropriate allowable deflection that corresponds with that. So this is our dead and snow allowable deflection with our dead and snow serviceability line load. This is our snow line load with our snow maximum allowable deflection. And we'll calculate two different I requireds, or minimum I's that we need. Now we can compare. We can see that this one is the biggest I, so we need an I, or moment of inertia, of at least this. I find it handy to write out myself a little chart. I am saying that I need an MR greater than MF, and I know my MF is 303.4 kilonewton meters. I need a VR greater than VF, and I know that VF is 134.9 kilonewtons. I need an I actual greater than the I required, and the I required is 238.9 times 10 to the 6 millimeters to the 4th. So let's go to the beam charts. Let's see what we can find. Let's open these charts and see what we get. So we know that they list the moments depending on what their unbraced length is. The distance between our joists was 1.8 meters. So there's 5 spaces, 9 divided by 5, we're going to get 1.8 meters. So we need to make sure that we're thinking about an unbraced length of 1.8 meters. The I is listed here, the I actual of the beams, and VR. So let's go through and take a look. None of these seem to have an I high enough of what we need. I think we needed 238, right? None of these work. Oh, we come up here, we've got a W460 by 60, has a VR of 746, an I of 255 times 10 to the 6 millimeters to the 4th. Not all of it's written here, but they do show it right here. And let's take a look what the MR is. Well, they say that for everything with an unbraced length less than 1.97 meters, it's governed purely by strength. It's not about buckling at all. So we can use kind of the easy peasy MR that they have, and that is 397 kilonewton meters. So this one seems to work. Let's see if there's anything lighter. Well, this 410 has a shear, an eye, and a moment that works. But look at this. 67 is how many kilograms per meter it weighs. This one's only 60. That means that this is actually heavier than this. I'm not going to use this one. I'm not going to use the W460 by 61. They don't make those as much anymore. It's hard to find them and hard to source them. Some plants might still have them on hand, but we wouldn't start there. We wouldn't put that on the drawings, and if a plant asked, maybe we'd switch it out for it. Everything else seems to be heavier, so even if it works, why would we use it? It doesn't seem like it would be a good idea or cost effective on our project. So I think a W460 by 60 is a really good choice. It meets our requirements. Let's go back and look at our steel beam. So I've got that here, and it's highlighted that it works. Now, my drawings showed a W410 by 60, and we've just found that a W460 by 60 is what works. Now, I used a design software to analyze this building. Might as well bring it over and show you guys what I used. So this is Etabs. This costs, depending on what version of the license you have, anywhere from $6,000 to $25,000 to purchase the license for this. I use this a lot. Etabs is kind of my go-to design software. And let's take a look. Roof. Well, there's, here is our beam. Well, in this, I've actually got a W460 by 60, but don't worry about that too much. Let's take a look at what this shows the shear diagram to look like. Look at this. That doesn't look like our shear diagram, does it? It looks a little bit different. This has analyzed it as a series of point loads on it. Some of you are going to want to do that for your project, for your beam. And I'm going to tell you, don't. It's more complicated, it takes more work, and it creates a very small difference, almost imperceptible cost-wise. Both beams on both versions of the drawings both weighed the same amount. We often, when we're doing this by hand, would treat it as a uniformly distributed load. I know, here's another one of those things that I am telling you crazy things that don't match up with all the things that we're doing every time. And that's, again, where industry standard and practice and knowing what's going on again and again and again is really handy. Most of these things used to be designed by hand back in the day. And when we did that, we would always do it treating it as a UDL. For a computer program, it is absolutely no more work, so we'll often treat it as the series of point loads. I am trying to show you the hand calculation versions that I want to match with the old methods that we used to do, because that makes our life a little bit easier to calculate it, and it was literally how we used to do it. So this is, again, one of those weird things that happens because I'm a pro at what I'm doing. You guys are going to do a uniformly distributed load on a simply supported beam. For I don't think you do a truss in this version. Well, let's now take our W460 by 60 and do it by hand. Let's calculate it out and see if we get these numbers for shear and moment. All right, so let's start up here. We want to try the actual calculations for a W460 by 60 with an unbraced length of 1.8 meters. That's the distance between the joists. We know that for steel, The bending reduction factor is 0.9. The Fy for hot rolled steel is 345 MPa. E is 200,000 MPa. G is 77,000 MPa. That's pretty easy. We can look up the member properties. Let's go to our steel section here. Let's find our W460 by 60. All right. Oh, no, one more page. Oh, I went too far. All right, W460 by 60. We can look up all the things we need here. We can look up the area if we need it, IX, SX, ZX. We can look up IY. Remember that for a beam, for the strength part, we care about everything about the x-axis, but for anything that has to do with stiffness, like say lateral torsional buckling of the top chord popping out sideways, we care about IY, or everything spinning about IY, or using this axis. So for stiffness, we're going to be using IY, but for stiffness of lateral torsional buckling, we'll be using IY. But for strength, we'll be using ZX, and for stiffness of the overall member in bending, we'll be using IX. We also have those big ridiculous numbers J and CW here. So let's pull this up here. We know that it's a class 1 or class 2 section, which means we get to use the plastic analysis. If it was class 3, there'd be funny little symbols beside us letting us know, and then we'd just use the elastic properties. That just means we get to use Z instead of S for our bending strength. So we were able to look up IX. We can look up ZX, IY for weak axis stiffness used for our top chord buckling, J, CW. We know that the overall length is 9 meters, but that the unbraced length is only 1.8 meters. So now we can go through this process of calculating MR. And MR has a few stages. First, we calculate what M is based on whether it's just plastic or elastic bending. So this is just our shape property times Fy. So we have Fy of 345 times our shape property Zx, and we get that MP would be 441.6 kilonewton meters. Then we need to calculate what is our buckling moment. At what moment would this want to buckle? So for that we have a big painful equation that looks like this, but we know that if we break it down and calculate this component and this component and this component, we can kind of start to keep track of things. So that's been done here in stages. You can go through and plug this into your calculator. And we get that MU equals 1,126 kilonewton meters. So the buckling moment is really, really high for this. So we want to see, is MU greater than about 2/3 of MP? It is. So that means our moment equation is this right here. 1.15 times our reduction factor times MP in brackets times what we know is very similar to our lambda factor in the columns. So basically what we're saying, but it has to be less than this value right here. We wanted to know what is the strength alone value, what is buckling alone value, and then is this somewhere in between? If it's really short, it's just governed by strength. If it's really long, it's just governed by buckling. And if it's somewhere in between, it's governed by a combination of both. So we can go through and calculate what it is when it's somewhere in between, and we get that it's 406.9. But look, 0.9 times just strength alone gives us 397.4. It looks like this member is governed by just strength alone. Now that makes sense. Do you remember when we looked at the beam table, it said that for any beam less than 1.97 meters long, or an unbraced length less than that, the value didn't change. This is what MR was. That's because we were in the zone where strength alone governs. We didn't have to worry about buckling at all. Basically, it's so stocky that buckling isn't going to be the thing that governs. So now we have calculated our MR value. All right, VR. VR, we know, equals our reduction factor times AW times FS. We know that FS is really just 2/3 of FY, and that's about averaging out the stress distribution that we see in the stress profile for a beam web in shear. The area is just the area of the web. We know what FY is. We know what our reduction factor is. This is some of the reason why this takes so long, is you have to highlight every individual thing and change it to show if it's a different font. We know what the depth of the beam is. We could look that up in the steel beam properties or in the steel section properties. And we could look up the web thickness. So that was in the same place where we got our I and our Z and our J and our CW. So we can calculate the area of the web. We can calculate what 2/3 of FY is. And then we can plug that in and we can calculate VR, and we get 745,945, or 745.9 kilonewtons, which matches what they had listed in the tables. So now a good thing to do is always write out for ourselves, does this beam work? We have a W460 by 60 beam. We have an MR for an unbraced length of 1.8 of 397.4 kilonewton meters, and that has to be greater than MF of 303.4. Seems to be correct. We have a VR of 745.9 kilonewtons, and it has to be greater than 134.9 kilonewtons. Seems like it is. We have an I actual in the X direction of 255 times 10 to the 6 millimeters to the 4th, and it needs to be bigger than the I required, because this is the minimum we need. We have to have at least this. And our I required is 238.9 times 10 to the 6 millimeters to the 4th. So it looks like our I actual is greater than our I required. So we've met all of the things we need to meet to say that yes, this steel beam works. So now we have gone through our steel beam and our steel column. Let's move on to our wood elements. Okay, let's take a look at our wood elements now. Let's take a look at a wood post and a wood beam. So we don't have a wood project to take a look at, so I'm currently working on a project that's out for pricing right now. And we're going to take a look at that. So you guys won't have access to these drawings, but I'll give you all of the relevant information you need. So this is a pretty basic construction building. It's wood frame with stud walls, wood floor. It's raised up. It's not on the ground, so it's got a raised up floor with helical piers, walls, and then trusses for the roof. We're going to look at a post on this exterior wall and one of the lintels on this exterior wall. So there are trusses that span from here to here. It's almost like it's two buildings side by side, because then there is another set of trusses from here to here. Just to give you a sense of it, I can show you what these trusses look like. So we're essentially going to design one of the posts here in this wall right here. So let's take a look at our wood column drawing. So here I've given you a small screen capture of the flooring plan. And I've told you what this dimension here is, and that's where the trusses above span between. So they come down on this wall, and they come down on this wall. We are going to be designing this post right here. There's a beam coming down on it that is only 800 millimeters long, so very short. And so this is a post, and then in this wall there are studs every 16 inches. Because remember, normal building has studs every 16 inches. That's just kind of how we build it, unless there's something else going on. So this post is going to pick up half of this beam, and then half of the distance to the next post. So if it's 16 inches to the next post, it'll be 8 inches that it's picking up. So we could figure out what its tributary area is from that. We need to know what its loads are. Well, there's loads written right here. I then grabbed that and plopped it down in our analysis here. So let's just start with the simple, easy stuff that we normally do. Let's do our sizing guidelines. You don't have it in the drawings, but I'm telling you that this post is 2.8 meters tall. Our sizing guideline for a wood post is H divided by 30. And we get that we need an element that is at least 93.3 millimeters deep. Width, we know, varies between 2 to 3, a half to a third of the depth, which means that we're going to end up with a 3-ply 2x6, or something that is 114 by 141. So that seems like a pretty good place to start on this. So that would be our sizing guideline, what it gave us. We'd put that on our preliminary drawings. So now let's take a look at what we would have done last term. Look at the snow load on this. There's all kinds of information they've given us here. There's live load in the attic zone. That's not applicable to what we're doing right now. There's a deck, there's a canopy, there's unbalanced loads, but we're not worried about that. We're designing for 2.72 kPa of snow load. So somebody's already taken SS and SR and all of the factors that we need to apply and figured out what our snow load is. So somebody's already done the work that we did learn to do last term. And then here is the roofing assembly. This has all been added up, and we end up with a total of 0.9 kPa for our dead load. We know that we're going to want the factored dead and snow load. So we multiply our dead load by 1.25. We multiply our snow load by 1.5, and we get 5.205 kPa. Our tributary area is half of the span of the trusses, and then half of the span of our lintel, plus half of the span to the next stud. So our tributary area is 2.415 meters squared. Well, that means we can calculate PF. PF is our load times our area, and we get 12.57 kilonewtons. We know that our unbraced length in the strong direction is 2.8 meters. And in the weak direction, it's fully braced. Because it's in the stud wall, it's not standing out there by itself, it is fully braced in the weak axis. If this post was out in the middle of the room with no wall around it, we would be very worried about that weak axis buckling mechanism. But because it's attached to the sheathing, we're not that concerned about it. We're worried about it buckling in the strong axis. So here we've got our free body diagram drawn. There's the height of our post, there's our applied load, and here are our reactions. We need to make sure that PR is greater than PF. We know what PF is for an unbraced length in the strong direction of 2.8 meters. Now we're going to go to the stud wall selection table to look up what value we need. Now you're probably thinking to yourself, why are you going to the stud wall selection table? Why wouldn't we go to the built-up post section? Because there is a built-up post section. Again, here's one of those things that I am telling you because I know this. Because it's not freestanding, the post would be a freestanding element. We want something that's been braced by the sheathing in the weak axes. So the studs are designed for that. The stud tables are sheathed on one side, and since columns are only load sharing, we can use the stud table, but then multiply it by how many plies we have or need. All right, so let's take a look at our table here for SPF number 1, number 2, for a post that's 2.8 meters tall. We get that a 2x4 would work. A single 2x4 would work, in fact. Then we actually could see that, so a single 2x4 works. Great. End of day, we can walk away from this. So the way they actually build things is that they would make that post match whatever the stud thickness is. The studs have been designed by someone else on the project, and they have said that this stud wall system needs to be 2x6s. Okay, fair enough. We're going to make ours 2x6s then. So this is the 2x6 category. So a single 2x6 works. Done. End of story. Let's walk away. Except if you look at the fine print about the design of these things, posts, we always make them 2-ply. It's the same way our beams, we always make them 2-ply. We don't go less than that. So this post, even though a single ply of 2x4 will work, we would make sure that it was a 2-ply 2x6. It's just what we'd do. It needs to match the depth of the wall, and we are always going to use 2 plies for it. Now, we now know that if things came up and it was difficult to build or there was odd things going on, we have some kind of space in our back pocket that we could make use of to refine this design if we needed to. So this is for a single 2x6 stud. We've got 2 of them. So a 2-ply 2x6 SPF number 1, number 2 has a PR of 83.4 kilonewtons. So I've summed up here why we did 2-ply and why we did a 2x6. Let's use our 2x6 SPF number, our 2-ply 2x6 SPF number 1, number 2 in our design. So we're going to try the actual calculations for a 2-ply 2x6 SPF number 1, number 2 built up post braced in the axis. So what do we know? We know that wood in compression has a reduction factor of 0.8. Oh, look what I have here, structural joists and planks. Let me go check and see that I did in fact update this. Yeah, so that's all right. Let's look at, I'm going to bring up for you guys these tables. I had first decided to do it as the 2x4, but then changed my mind. So let's take a look. 2x6, right. So we have a smaller dimension of 38 and a larger dimension of 140. So structural joists and planks is correct. So I have this right, but this should just say 2x6 or 140. All right, so we can pull off from our tables that FC, which is the compression value for structural joists and planks strength properties tables. We get FC of 11.5 MPa, and E05 is 6,500 MPa. That's on table A out of all of those tables. The wood factors, well, duration, it's standard. Case, it's case 1. Service condition, it's dry for both compression and buckling or stiffness, and it is untreated, so just a ream of 1s. Normally, we check both weak and strong axis failure mechanisms, but we are fully braced in our weak axes. So it could fail by strength, but our strong axes could fail by the same strength calculation. So we only need to check the strong axes because it's the one that could possibly buckle. We know our member is 38 by 140. We know that its height in its tendency to buckle, which is the strong axis, is 2.8 meters tall, and its unbraced length for weak axis is 0 because it's connected to the sheathing. The equations for wood columns is very similar to our steel one, where it's got a component for strength, it's got a component for buckling, and then it's got a component for a transition in between those two governing failure mechanisms. So we calculate, we know our reduction factor. We calculate a capital FC, which is really just taking the FC we looked up off the table and applying some of the wood factors. We have a size factor, and then we have our tendency to buckle factor. We can start to break this down. Well, we know our reduction factor is 0.8. Our capital FC is just our lowercase fc times our factors. So we can calculate that. We've got 11.5 MPa still. Our area is 38 by 140. I have a 2-ply. So I have done it similar to how they did it in the tables, where I'm going to calculate 1 and then double it, simply because I'm going to match the tables as close as I possibly can that way. I did just want to check one thing. We have, sorry, I just want to check one quick thing here, folks. Yeah. My computer's being very slow, I apologize. All right. So we're going to calculate 1 ply at a time and then double it to get our 2 plies. We have our area is our width times our depth. We've calculated our capital FC. We can calculate our CC, which is the ratio of length to dimension. In our strong axis, it's 20. In our weak axis, it's 0, because remember, our unbraced length is 0. Our size factor is 6.3 times our depth times our width to the minus 0.13, but it needs to be less than 1.3. We can calculate that out. Our buckling factor, or KC, varies in the weak axis and the strong axis, but we've already said that the weak axis is going to be very, very strong because it's connected to the sheathing. So this is similar to our lambda factor that we calculated with steel. And here it is in this big, ugly, messy equation. It's all of the elements are written in here. And we can calculate 0.677. And then we can calculate the strong axis PR, or capacity of this member, by multiplying our reduction factor, by our strength, by our area, by our size factor, by our buckling factor. And we get 39.1 kilonewtons. So that means that for a 2-ply PR, we've got 2 times 39.1, or 78.2 kilonewtons. It's not exactly the same as doubling the posts in the calculations for the stud tables. I haven't determined exactly why, but I do know that when I use the wood analysis software, it matches what I've calculated here by hand. For a 2-ply stud in a wall, this is what it determines. Let's open it up. Open up my column. Sorry, I'll bring it over to your side in just a second. So here we have it's the height, that it's built up, what our dimensions are, that there's 2 plies of it, and what are that it's connected together nicely. I wonder if that would make the change. Right, I know exactly what the difference is, why the stud is different. The stud is being treated like it's a stud with the elements adjacent to it. Would you take a stud in a wall that's a post as a system of case 1 or case 2?
Oh, I think it meets the definition, probably.
But when I calculate it out, I still don't get the same answer it does.
Oh, sorry. Yeah, definitely would. A stud is a system case 1.
No, but it's a post. The post in the wall that's replacing a stud.
Are you sheathing it? Are you applying sheathing in your woodworks?
Yeah.
Because
yep,
once
continue.
it's a stud in a wall, it can only buckle in the strong direction.
Yep, I know.
Huh.
But I'm getting Woodworks and I both get different answers from what's in the tables for a single stud.
Oh.
By itself. So you can see that they also get the same value as us. So here it is here. Don't worry about that one. That's for the weak axis there.
Mm-hmm.
But here is our 78.23, which is what we calculated.
And you just did you did a 2-ply.
Yeah, a 2-ply, which is what I get when I manually calculate it as well. Actually, yeah, 78.2. Whereas the tables, sneaky little tables, gives us for a single ply 41.7, which would give for 2 of them 83.4. So I thought, in theory,
is 5% or 6%. It's not a system factor.
Exactly. So I thought, well, what if I multiplied it by the different system factors of 1.1 or possibly 1.4? Because we're going to see a built-up beam has its own system factor that we will apply to it. But it doesn't work out. If I take our what is it, 79.2 times 1.1, we get something much higher. So I can't quite correlate how they've gotten those two separate values, but I feel pleased that the software that the Wood Council actually produces matches exactly our hand
I wonder
calculation.
if there's a difference in the assumed eccentricity. There's a built-in assumed eccentricity of 1/6 of the member dimension.
But that would be in Sizer. Sizer matched my hand calculations.
And did you put a?
No. No.
Oh,
No, I did it as basic could be. I did it as plain as you could imagine.
interesting.
So you can see that you can get small discrepancies in these things. What we want is to be pretty conservative about things, but look at our load. Look at the load we had in this. The reason I am not fussed about this at all, maybe I would be if we were getting different answers on our single 2x4 that we said could work. But we've got 2-ply, look at this, I didn't even write it in there, 2-ply, 2 plies of 2x6 SPF number 1, number 2. So, does it work? PR needs to be greater than PF. We've got a PR of 78.2. This is the lesser of the two values, what we've calculated out. So I feel comfortable that we're using the conservative value. PF is only 12.57. So yeah, it seems over-designed, but the reason we're doing two 2x6s is because of the way we build the building. So again, I'm trying to show you ones that we calculate out, but also trying to give you a little insight that other things come into play for these things, and knowing how things go together, which honestly can only come with experience. That's all I can say. Some of this really just has to come from experience. I will give you questions. I haven't even given you ones as difficult as this, specifically so that you didn't have to go try to find what you were picking. I actually gave you things specifically to check for that reason, because you couldn't possibly know some of these things. I'm sure some of you have been builders and it's a little bit easier for you, but the rest of you couldn't know that because you don't have the experience. So that's why I usually try to give you an element that you're checking, the actual one you're checking. Okay. Let's take a look at our wood beam example now. So it's the same drawing set. We're going to do the lintel that frames onto that post. Now, a lintel is just a fancy name for a beam that goes above a window. So this goes in the wall above a window. Steel, we know we infill with other things, usually stud walls, and the windows kind of get attached to that. But in a house, we have our roof and we have our floor, but our window is down here. So we'll put another small beam, or we'll put the only beam in the stud wall at the top of the window height. Sometimes they'll put them up higher depending on how they're building it, but most of the time they'll put it down in the height of the window. So we've got the span from here to here. We know what the length of the lintel is. So here's our lintel right here. It's only 800 millimeters wide. Let's go to our second page. Very slowly. Let's take a look at our sizing guidelines. Rule of thumb says L divided by 14 for a wood beam. We're only 800 millimeters long. It's just the shortest, like it's about this big. So its depth needs to be at least 57 millimeters deep. So a 2x4 seems really good at 89 millimeters deep. We know the width is somewhere between half to a third, or 28 to 45. So a 2-ply seems like it would be pretty conservative. Here's the thing, for lintels and beams, we always do a 2-ply anyway. We're always going to do a 2-ply for beams like this. So 2-ply, 2x4, SPF number 1, number 2. Why is it SPF number 1, number 2? Because that is the most ubiquitous lumber that we use in the building industry for kind of this scale of construction. Not mass timber, but if it's inside your building and it's not fancy and nobody's going to see it, it's SPF number 1, number 2. Just think of that as a given. We have another uniformly distributed load on a simply supported beam, so those equations that we did for the steel beam stay the same. We've already looked at our snow load and our dead load, and we've already figured out our factored dead and snow load was 5.205 kPa. We know that this is a beam, so we're going to want to look at serviceability as well, or our serviceability dead and snow live load and our serviceability snow load all by itself. For snow, that means we get to use the importance factor for serviceability, which is 90% of the total snow load, or 0.9. So our serviceability dead and snow load is 1 times 0.9 plus 0.9 times 2.72. Our snow load all by itself is 0.9 times 2.72. We know that the length of those trusses was 8.05 meters long. This is picking up half of the roof. The other half of the truss is going to the other wall. So its tributary width is 4.025 meters. That means we can calculate our line loads, our uniformly distributed line loads, both our factored one, our serviceability dead and snow, and our serviceability snow. So here are those calculated out. So it's the loads multiplied by the tributary width to give us our line loads. Here is our free body diagram showing the dimension, the reactions, and the uniformly distributed line load. We know that for simply supported beams, we have pretty easy means of calculating the maximum shear and the maximum moment, and we know what the shear diagram and the bending diagram looks like. So here those are written out. We can calculate our maximum shear, and it's VF times the length divided by 2. Or we end up with a shear of 4.38 kilonewtons. Our maximum moment is WF times L squared divided by 8, or we end up with a moment of 1.68 kilonewton meters. We can calculate our maximum allowable deflection. Now look, I have used L divided by 240 and L divided by 360. These are not the exact same as what are listed in the serviceability charts. I would make sure I gave you what serviceability criteria to use, because I know it's not always clear, or else I'd be very explicit what one you were looking at. There would be no ambiguity. I would tell you there was drywall in it, if it could be cracked, it was a roof. I would be very, very, very explicit. But I am telling you that this is often what gets used. It doesn't matter what's in those charts, that often people will, just without thinking, use 240 for dead and live or dead and snow, and 360 for live or snow. And it's more conservative. These are the most conservative options. So a lot of the times, if there's no difficulty in designing this, or if there's no headroom constraints, and I don't think it's going to make a big price difference, which it wouldn't in this case, I would just probably still use the 240 and the 360. Again, I would be very explicit on what you have to do. I'm just telling you, I'm trying to show you what actually gets done in the calculations that people do. Remember, in wood, we don't just calculate the I required simply because wood has so many different E values that we don't know what member or what type of lumber we're picking yet. We haven't really come down to that conclusion. We haven't picked out what design chart we need to use. So we figure out what EI we need, what the EI required is. So for dead and snow together, I'm using my deflection calculation equation and rearranging it to find ES. So instead of ES being here and D being here, I've rearranged it, and we know what the allowable deflections are. We just calculated these right here. So I rearrange it and I solve it to find out what the ES I need is. So this is the minimum required ES. Remember in our steel building, even though we were using 240 and 360, our dead and snow together was the governing case. Well, look at this one. The ES required is governed by snow all by itself. So it really does depend on the loads and the criteria that change. So I used the 360, but if I used the 300, this would go down, and maybe then this one would govern. If the snow loads were different, it wouldn't be clear which one governed. So that's why we actually have to go through and calculate out both. But now I have an MF, a VF, and an ES required. This is the minimum of what I need. Let's go to the sawn lumber built up beam tables. We have SPF 2x6, and then look here, they have 2-ply, 3-ply, 4-ply, 5-ply. This is the number 1, number 2 category. I've clipped it off there, but let's pull it up here. So here's the chart that I'm looking at. And there was the select structural grade, number 1, number 2 grades. So we're down here using this. You can see 406. So this is what I've cut out here. It's the number 1, number 2 grades for SPF of a 2x6. Let's come back to our wood beam. And we have a 2-ply beam, which is, remember, we need at least a 2-ply. Has an MR of 4.06, a VR of 14.7, and an ESI of 165 times 10 to the 9 Newton millimeters squared. Well, let's take a look. 4.06 is greater than 1.68, 14.7 is greater than 8.38, and 1.65 is greater than 24, roughly. So it looks like a 2-ply 2x6 is a really good choice here. Now, I'm going to tell you that this project happens to have a 3-ply 2x10 in it, but that's because of just how they're building it, what's going together. There's other lintels, and now they're all just standardized, or they all have the exact same lintel. But we're going to design the 2-ply 2x6 SPF. So we're not going to do what's on the drawings. We're going to design. We're going to try to match these calculations right here. So let's go to the third page. And we want to do the actual calculations for a 2-ply 2x6 SPF number 1, number 2 that spans 800 millimeters. We have our depth. We have our width is 38 millimeters, but there's 2 of them. Our net area is the whole section, or 10,640. S is BD squared divided by 6, and I is BD cubed divided by 12. So those are all 3 different shape properties we make use of. Wooden bending and shear. We know that the reduction factors are 0.9. This is joist and plank grade section, so we can look up FB and FV and our E. Our factors. I had forgotten this, that built up beams have a system factor of 1.1. Let's take a look at this right here. Let's go down and look at system factors. So system factors, there was case 1 and case 2, which we talked a lot about, and machine rated lumber, which we don't use. But then over here, look at this, built up beams. So we have a built up beam, and for bending and longitudinal shear, 1.1 is our system factor that we can apply. So that's great. We get to increase the strength of our member a little bit. So our system factor for both bending and shear is 1.1. Our service factor is 1. Our treatment factor is 1. Our our KZB and our KZV. Remember, that was also from a chart. Let's bring this up again. KZ. For columns, we have to calculate it. But for beams, we get to pull it off of this chart. We have a larger dimension of 3.8, and we have a larger dimension of 140, and we have a smaller dimension of 38, or 76. But they're talking about an individual, so remember this is the size factor. We want to look at a piece on its own because this is the odds of a knot being hidden in it. So before we screw it together, it's all by itself, and we can see the perimeter of it very easily. So we have 38 by 140, so we're going to have a KZB and a KZV of 1.2. So KZ, of 140. Sorry guys. Of actually 140 is 1.4. So we've got 140 right here, 1.4. I don't know why I was pointing to this, but 1.4 is very much correct. Let's bring up this again. So we've now got our KZB and our KZV. The calculations for shear and moment are a little bit easier. Remember, buckling is rarely a concern because it's usually attached to a bunch of things. In this case, we're attached to some stud above, maybe we're up tight to the top, there's sheathing on the side. It's going to be hard to make this thing buckle in its weak axes. We have our reduction factor, our bending strength, with all of the factors in on it. So 11.8 times our 1.1. Then we have our shape property, which we calculated further up there. And we have our size factor of 1.4. So we can calculate that we have an MR of 4.06 kilonewton meters, which is exactly what we saw in the chart. Shear, it's very similar to what it was for steel and similar to the general thought process. We have a reduction factor, our strength value times a shape property, and any other factors. Well, our strength is FV times all of these wood factors, which for us is really just 1.1. And then the odd thing with shear is we're taking 2/3 of the area, or it's 2/3 of that stress distribution that we saw when we looked at the steel web. So VR is 14.75 kilonewtons. We can calculate the ESI. E has some factors applied to it, but both of those factors were 1. E is a shape property, so we can calculate ESI is 165 times 10 to the 9 Newton millimeters squared. These all match what we saw in the table for bending. So now we write out for ourselves, does a 2-ply 2x6 SPF number 1, number 2 lintel work? Well, MR is greater than MF. VR is greater than VF. The ESI actual is greater than the EIS or ESI required. So this is a member that works. So we've gone through a few different examples now. I was struggling on whether I would also do concrete beam examples for you. And I've been thinking about it because, as you saw even with these, all of these examples I've ever given you are simplified. Some of you are hungry for more complex ones, but that's not fair for kind of unifying things across the class. The simplifications that I would have to make in the concrete ones would be a lot more. We've seen now that concrete beams actually do tend to have moment connections at the end, and so the actual stiffness of them is important. The design process for designing concrete beams, for finding MF and VF is very, very complex. I don't think it's going to add anything to the course to go through that. That said, keeping that in mind, the examples we did last week for the columns and beams in concrete were pretty simple. I don't think you guys would need to go much further on that. So with that in mind, I think we're done. We're done the hard stuff. You guys have all the examples you could possibly need to ace my course. And I promise you, in the past, people have gotten 100% on my exams. So you have all the information you need to ace it. I've actually given you more than most because all of these examples that I just did for you today, I created for you guys. Those were all brand new examples that I spent the past 2 days making for you guys. Next week, Dave and I, unless it changes before Tuesday, the voting's pretty close. It looks like it's going to be reciprocal frames that Dave and I do for you guys next week. And then in week 12, I'll show a video of the beams being tested. There's a chance we could switch to catenary and fabric structures. If so, Dave would be giving that lecture alone. Steel castings is my lecture. There's only been one vote for steel castings, which really surprises me because those are some friggin' cool things. There's some really neat stuff in the steel castings. Maybe my description wasn't good enough. Steel castings, making European technology our own. Steel castings, showcasing architectural steel forms in architecturally exposed forms in steel. I don't know, maybe those are better descriptions. Complex representation of complex geometry is always just a fun one because as we're getting more and more complex projects, how do we take what used to be just 2D drawings and present that to contractors and make them say, okay, go build this. You have to be able to bid it and then build it with only a set of 2D drawings to build this complex thing. We end up wasting a lot of our time as the design team trying to take this complex thing and flatten it into 2D for the contractor to look at it and bring it back into 3D. Maybe we should be working in 3D. Now, I know you guys are thinking, yeah, BIM exists. Of course, Shannon, this is all very silly. We all know how that works. Except contract documents don't work that way. We still produce an intense amount of stuff for 2D. And usually a lot of the, some of that stuff was supposed to be on the contractor. So there's kind of a redefinition of things there. I also love the reciprocal frame lecture. That was super fun. I love giving lectures with Dave. That one's ours. We gave it to 500 people in October. It was a podcast group in Australia got us to do it, so that was super fun. So we'll see which one you guys pick, and Dave and I will record that next week for you guys to watch, and then the week after we'll test some fun, cool beams to failure. Okay, bye team.